Welcome to the next lecture of the CBNST. In today's lecture, we will talk about another method to solve algebraic and transcendental equations. Today we will talk about Newton-Raphson method. We have already seen bisection method, regular falsi method and iterative method. And today we will talk about Newton-Raphson method. This is one of the most commonly and widely used method because it gives the better convergence. So we reach to the perfect answer, to the perfect, nearest to the perfect solution very quickly. So let's say, what is the method? For fx is equal to 0, if there exists an interval a comma b such that at f at a and f at b, the signs are opposite. So that means if the function's value at one endpoint and the function's value at other endpoint, if these are opposite in signs, similar condition to the previous methods, we have seen this into the bisection, in the regular falsi as well as into the iterative method. So this is one of the primary condition. Then we have this formula to find out the solution. This is called as the Newton-Raphson solution formula. Xn plus 1 is equal to xn minus f of n divided by f dash of n. This is the first derivative of the function. Let's understand this with the geometrical concept. Let's say this is the fx, the curve representing the function. This is the x-axis and y-axis. Let us consider that we have the initial approximation, let's say x0. How we can get this initial approximation? This initial approximation can be any point in this interval a comma b. This could be a, this could be b, or any point in between a comma b can be considered as the initial approximation x0. So from this initial approximation x0, we will draw a perpendicular, and this perpendicular will cut the curve at some point. This point will be known as f at x0. So this can be considered as the intersection point f at x0. From this intersection point onto the curve, we will draw an asymptote. We will draw an asymptote basically. So this line, this is the asymptote that has been created from the point of the intersection. This line will cut the x-axis at some point, and this will be our new approximation root. So this is x1. Now we'll repeat this process, and from this new approximation root, we will draw a perpendicular onto the curve. Again, this perpendicular will cut the curve at some point. This will be known as f at x1. From this point, we will again draw the asymptote. Let's say if we draw the asymptote, so it's not actually looking like an asymptote, but we'll have to imagine that we are drawing an asymptote from this point, and if this asymptote will cut the x-axis at some other point, let's say x2. So now we will repeat. We'll again draw a perpendicular, and at the intersection point onto the curve, we'll again draw the asymptote. So in this way, we are approaching towards our actual solution, and you can see we are approaching much faster as compared to other methods. So this is the formula that we'll be using into the Newton-Raphson method. Let's say our first iteration, if our first approximation is x0, then we'll put x0 into the formula, and just by putting x0 in the formula, we can evaluate x1. In the next approximation, that is x2, will be achieved by putting x1 in the formula in place of this n. So now f dash x1 will give us the new approximation root x2. So we'll keep doing this till the desired accuracy. Now let's do this Newton-Raphson method. Let's understand this with the help of an example. Now let us solve this example and understand the Newton-Raphson method. So this is the function fx is equal to x square minus 5x plus 2. We need to find out the real root of this equation, correct up to 4 decimal places. So let's find out this interval a comma b with the help of the hidden trial method. Let's say if I put f at 3, so this will be I'm using just hidden trial method. We can start from 0 also. I'm starting from 3 here, so this will be 9 minus 15 plus 2. So this will be minus of 4. It's a negative value. So let's move further. Let me put f at 4. And you can see this is 16 minus 20 plus 2. So this is coming minus of 2, another negative value. We need to do it more. So let me take it f at 5. So this will be 25 minus 25 plus 2. So now this is plus of 2. We have got a positive value. So we can see that we have a negative value at 4 and we have a positive value at 5. So our initial interval will be 4, 5. Now from 4, 5, our first approximation could be anything. We can take 4, we can take 5, we can take 4.5, the midpoint of this interval. We can take 4.1, 4.8, any value we can take in this interval. So let me begin just by taking 4 as my initial approximation. So I'm taking here x0, I'm taking here x0 as 4, right? And before I begin, I need to find out the first derivative of the function. As in the formula, we need the first derivative. So let me find out this f dash x. This will be 2x minus 5. I hope you are aware about the differentiation. So this is x square will come to 2x, minus 5x will come minus 5, and this is a constant that will be vanishing. So this is fx and this is f dash x. Let's start our first iteration. So in the first iteration, we will be finding out the value of x1. This will be equal to x0 minus f at x0 whole divided by f dash at x0. What we have taken as x0? X0 we have taken as 4. So let's begin. X0, that is 4 minus, okay, function's value at 4. So we need to substitute 4 here. So this will be 4 square minus 5 into 4 plus 2. This is whole divided by, we'll keep this 4 into the derivative function f dash. So this will be 2 cross 4 minus 5. So this is coming. Now we can use the scientific calculator and we need to find out the value of this. So let me find out what is the value of this x1. So x1 is 4.6667. So this is our first approximation, that is x1. So now we'll do the second iteration. We evaluate x2. Obviously, how we'll get x2? This is x1 minus f at x1 whole divided by f dash at x1. So this will be 4.6667 minus function's value at 4.6667 divided by function's derivative's value at 4.667. In the same way, we had obtain these values. We will substitute this 4.6667 into this fx to obtain this numerator, and we will substitute this 4.666 in place of x in this f dash x to get the denominator, and we can solve. So let me see what is the value of this x2. So this x2 is coming 4.5641. So this is coming 4.5641. In the same way, now we need to go further and we need to find out the next iteration, because we have not achieved to the desired accuracy till now. So we need to get this, we need to execute our third iteration. So we'll do the third iteration. We'll evaluate x3. x3 will be x2 minus f at x2 whole divided by f dash at x2. So this is, what was the x2? This was 4.5641 minus function's value at 4.5641 and derivative's value at 4.5641. So we'll substitute these values into the original equation and this will be into the derivative. So let me see what is the x3. So the third iteration, x3 is coming 4.5616. 4.5616. So now we can see after the third iteration, we have got the result correct to 2 decimal places, but we need to do it till 4 decimal places. So we need to do next fourth iteration also. So let's move further and go for the fourth iteration. So in the fourth iteration, we'll find out x4. This is x3 minus f at x3 divided by f dash at x3. What is x3? x3 is 4.5616. So this is 4.5616 4.5616. In the function we'll substitute 4.5616 in place of x. In its derivative also we'll substitute 4.5616. So in the function 4.5616, in the derivative 4.5616, and we'll evaluate the x4. So let me see what is the value of the x4. It's 4.5616. So this is 4.5616. Now as we can see by comparing the last two iterations, the value of this x4 and the value of this x3 both are same till 4 decimal places. So now we have got our result correct to 4 decimal places. After 4th iteration, so we will see that the real root of this given equation correct to 4 decimal places is 4.5616. So this is how we use the Newton-Raphson method. I hope you have understood the method. It's a geometrical interpretation on how we will be able to solve the questions on this. So that's it for the today's lecture. We'll meet into the next lecture with some more methods of the numerical techniques.